In this video, we're going to be talking about garbage collection. You can find information about garbage collection by either going to my garbage collection notes or by looking at section 7.7 in the Scott textbook. So there's basically problems with garbage collection, meaning reclaiming memory that's been allocated off the heap. In many languages like C, C++, leave it up to the programmer to deallocate memory. And that can be tricky. As you well know, there's two types of problems. One is if you prematurely deallocate memory, you may get dangling references. And if you forget to deallocate memory, you get memory leaks. So in an effort to help the programmer with this, many modern languages like Java and Python provide automatic garbage collection, whereby the programmer is still responsible for allocating memory, but the runtime system is responsible for deallocating memory. And there's essentially two types of garbage collectors. The first is called reference counting, and the second is called trace collection. So reference counting involves keeping account of the number of references to each block of memory and reclaiming that memory when the number of references reach 0. So as an illustration, down here you can see we have two allocations of memory. We're allocating first a string to A with the string hello, and when we do that, it gets hello gets a memory count of 1. So we can represent that. Let's do hello, and it has a pointer from A, and now we allocate to B a string world, and so world now has a reference count of 1. Now we say B equals A, so now B also points to hello and no longer points to world. You can see hello now has a reference count of 2, world has a reference count of 0, and so we can reference garbage collect world. Now the way we implement reference counting is that at the start of each block of memory we place a 4-byte counter. So actually for hello there would be a counter up there, and the same thing for world. There would be a 4-byte counter at the top. And then between, or actually before and after each pointer assignment, the compiler inserts statements to increment and decrement the counts. In fact, there are some languages that provide so-called smart pointers. C++ has such a smart pointer in its standard library so that you can actually not have to do garbage collection yourself, but the pointers will take care of the addition and subtraction on their own. And you can look that up if you're interested. We're not going to discuss that further. Okay, so there's a number of advantages and disadvantages for reference counting. First of all, it's simple and it works well for strings. It also uniformly distributes the cost over a program's execution, so you don't see annoying pauses, which you will see with later algorithms. It has a huge disadvantage though, which is it does not work for circular structures. So let's illustrate or take a look at that. If we go and look at this example here, we see that Stooges is a pointer to a circular list consisting of the elements Larry, Moe, and Curly. And when we assign nil to Stooges, thus breaking the link to the front of the list, you can see that we decrement the number of references to Larry from 2 to 1. Unfortunately, because the list is circular, all the elements of the list still have one reference, and therefore it's impossible to garbage collect it. So circular structures lead to an inability to garbage collect them. The second disadvantage associated with reference counting is you have to add increment and decrement statements before and after every pointer assignment, so it triples the amount of storage associated with each pointer assignment. So to combat the issue with circular structures and also to get rid of some of the overhead associated with reference counting, another type of garbage collection is something called trace collection, and that means you try to periodically sweep through memory and see whether there's any trace of pointers to objects, and if they are, they're still considered live. If there's no pointers to them, they're considered dead and their memories reclaimed. The most basic and straightforward type of algorithm is called mark sweep, which is commonplace in many functional languages, which Lisp is the most prominent example of, but you also tend to find them in Java and some other languages. We'll see that it's necessary that the language be strongly typed. I'll explain that in a moment. It's not as possible in languages which aren't strongly typed, such as C and C++, although people have still written partial garbage collectors for such languages. And if you're interested, you can look at the internet. The Xerox Portable Common Runtime environment is one such environment for doing some partial garbage collection. So the basic idea behind mark and sweep is that it's a threefold process. It's a recursive algorithm. So we start out and we walk through the heap and we mark every block as useless. And then we go outside the heap. So let's actually go to an example. So let's here draw our heap. Let's draw some blocks of memory. Let's have some of them reference each other. And now outside, so this is our heap. And now we have some functions that have been called. So this is the stack. We have stack frames. And we also have globals. So each of these may have pointers into the heap. So what we do is for each of them is we engage in a depth first search. So let's say that we started from our globals first. So we would go through and we would mark what we encountered as useful, which in this case is these two blocks. Then we'd go into our stack frames and we'd follow this link. And when we came down here, we would see that this block was already been marked, and so we wouldn't have to go any further. So that would take care of our second step of walking through the heap. Then in the third step, we walk through the heap again and move every block that's still marked as useless to a free list. So in this case, this block right here is not been checked off, and so it would be moved to a free list. Now, the reason that we need to have a strongly typed language is that we need to know at runtime, we need to be able to look up a description of each object to find out what its pointer fields are. So in order to follow this pointer right here, we need to know that this field is a pointer field. Now remember, in strongly typed languages, you are going to be able to somehow you're going to have a description of that object. Typically, it's going to be kept at runtime. So there may be a tag associated with it that allows you to, so you may have a tag that is going to give you a pointer to some table where you can look up the description of the object and find which fields are pointer fields so that you can recursively follow these fields. Okay, so the advantages of mark sweep is that it has less overhead than reference counting. You don't have to associate the 4-byte counter field with each memory block, which can be pretty high if the memory block isn't big. Plus, you don't have to instrument every pointer assignment. And a big advantage is it collects circular structures. However, the disadvantage is that it can cause long pauses because you wait until memory's essentially been exhausted before you go in and do it. And in real-time applications like graphical user interfaces, this is unacceptable because all of a sudden your graphical user interface freezes. The second problem is it does require a strongly typed language, hence it doesn't work well with a language like C or C++. Essentially, you're probably going to have runtime information about each memory block that allows you to reference or find out what its pointer fields are. And third, the implementation tends to be tricky because you're doing this algorithm when you're essentially exhausted free memory. So it's not like you have a lot of memory available for your bookkeeping operations, such as doing depth first search. So what you typically end up doing is you are going to reverse your pointers. So here we have an example, and what we normally do is we just keep track of a previous pointer to the previous block of memory and a pointer to the current block, and we reverse our pointers. So here's an example. We have memory block R, and it points to S and T. So in B, you can see that we are now going to be visiting block T, so right here. And what we've done is that we've made this right here point to whatever previous used to point to. So that's what we have, actually not here, this one that used to point to T is now pointing off to what previous used to point to. This previous right here is now pointing to R, and we've moved current to point to what this T used to point to. Now in C, what's happened is that we have gone and we're looking at memory block U. So we've updated current to point to U, and you can see here that the middle one pointed to U. So we now are going to point back to R with the one that with T. So we reverse the pointer from U, and we now have it pointing to R. And you can see here that's what previous used to point to. It pointed to R. Now previous is made to point to T. And this continues with us as we advance our depth first search. We keep reversing the pointers. At each time, there's at most one pointer in each block that's been reversed. And when we go back to that block, we may have to somehow search to find which of the pointers has been reversed. That's a little bit of bookkeeping, but that can be easily performed. And then when we return, we also have to be able to reverse things again. So for example, in D, we have finished our search. We've gotten to the bottom, and we are looking at X, and we now need to be able to go back to U. So we use the previous one to return to U, and now we are going to reverse this pointer right here so that it points back to X. And we're going to make our current now point to U, and our previous is going to be updated to point to T. So the implementation is a bit tricky because we don't have a lot of space. So to try to reverse some of the issues associated with mark and sweep, another technique was developed called stop and copy. And it's a technique that eliminates memory fragmentation by compacting storage. So the easiest thing to do is to first illustrate, and then we'll come back and look at what it does. So again, let's draw out our previous heap. So we have 4 objects, and we'll have pointers, and we'll have our stack frame with a pointer in here, and our globals, one of which has a pointer into here. Now what we do with the stop and copy is we have 2 halves to memory. So right now this is the full half, this is the empty half. When we start garbage collection, we again look at each pointer that's external to the heap. So again, if we go into the globals, we start and we see this object. And what we do is we mark it as useful, we move it down to here, and we also keep a pointer down to there for the time being because we may have to update pointers. You'll see that in a moment. We now do our depth first search and mark this block also as useful. Move it down to here and also leave a pointer. That exhausts it for global, so now we follow this pointer from the stack frame, and it comes in, moves this memory block down to here, and creates a pointer to it. Now you can see that this pointer gets followed, and it sees, useful, so it's already been updated, and you can see the pointer is now right here. So what happens is we both move this block down to here, and the pointer is updated to point to right there. Okay? And the same thing actually happened when we moved this block right here. We also, through our depth first search, would create a pointer from this first block to the second block, and that can be done directly during the depth first search. So that's the basic idea behind stop and collect, and as you can see, it both compacts memory. You can also see that it only did, in effect, step 2, the depth first search. It didn't march through and mark everything as useless, nor did it have to do the third step of sweeping through and reclaiming this unused block. The reason it didn't have to is that this whole block is going to become empty after this step, and all new memory is going to be placed into the second block. So the advantages of stop and copy is it eliminates memory fragmentation, which can happen when you have a lot of memory allocation, and it eliminates steps 1 and 3 in mark and sweep. Its disadvantage is that it halves the heap size. Now this isn't necessarily as big a disadvantage as you might think, because in today's world most of a program's memory is in so-called virtual memory, and only a part of that virtual memory is actually mapped to physical memory. So when you halve the heap size, you're really only having the virtual memory size, and it's not necessarily as big of a disadvantage as you might think, because the physical memory that's associated with the process can just be mapped to whichever half of virtual memory is currently in play. Okay, so there's a third technique called generational collection, and its key observation is that most dynamically allocated objects are short-lived, and they can be placed in a so-called nursery region, while longer-lived objects can be placed in older regions. So what we do with this strategy is we divide memory into multiple regions, and often it's just 2 regions, a so-called nursery region and an older region. And when we need to garbage collect, we start by garbage collecting the nursery region. And we only garbage collect the older regions if we can't reclaim enough space from the nursery region. Then after some number of garbage collections, which is typically 1, we promote blocks to the older regions. So if they survive the reaping, so to speak, they get promoted pretty quickly. One complication is that we don't want to have to we're adding a third source of pointers, external pointers. We have pointers from stack frames, pointers from globals, but now we also have pointers from old regions to new regions, and we don't really want to sweep the old regions each time. And the reason is, it turns out through empirical observation that there's just not that many pointers from the old to the new regions. And so what happens is that typically the compiler will generate code at each pointer assignment, so a little like reference counting, and it will check to see whether the new pointer is an old to new pointer, that is going from an old region to a new region, and if it is, it will add the pointer to a special list that's accessible to the collector. So the collector not only will sweep through the stack frames and the global variables, but it will also sweep through this special old region pointer list. Now, the advantages of this generational collection is that it decreases the length of the pauses even further, because you're not even garbage collecting half the area. You're only garbage collecting perhaps a smaller nursery region. The disadvantage is it's much more complicated, because you have the multiple regions, you have the pointers from the old regions to the new regions, and you have to now go back to instrumenting your pointer assignments, so it has higher overhead. So each of these three things, mark sweep, stop and copy, and generational collectors, they all have their advantages. You see them all currently in operation, and hopefully you now have at least a general idea of the various garbage collection strategies available to a compiler writer or someone who implements it for a runtime environment, such as for a scripting language.